Let us continue D block elements. In the D block elements, we will take 3D series. In the 3D series elements, divalent into trivalent we will see. Divalent into trivalent tendency we will see. Now, for scandium, E0 value is not given. For titanium, divalent into trivalent is plus 0.37 volt. For vanadium, plus 0.26 volt. For chromium, plus 0.41 volt. For manganese, 1.57 volt, minus 1.57 volt. For iron, minus 0.77 volt. For cobalt, minus 1.97 volt. For nickel, value not there. For copper, value not there. For zinc, value not there. Set. Now, scandium plus 3. Scandium plus 3 is having what configuration? We'll see. So, scandium atomic number is 21, electronic configuration is argon 3d1 4s2. So, scandium will have most stable oxidation state plus 3. So, scandium shows plus 3 oxidation number, that is having noble gas configuration argon. So, for scandium plus 2 is easily converting into plus 3, and also scandium shows mainly plus 3 oxidation state. So, zinc we will see. Zinc electronic configuration is argon 3d10 4s2. So, Zn2 plus we will take. Zn2 plus. Zn2 plus if we take argon 3d10, that means pseudo noble gas configuration. Zn3 plus in the sense argon 3d9 unstable configuration. So Zn3 plus is not possible. Zn2 plus only possible. So zinc 2 plus into 3 plus not at all possible. Okay. Next, we'll take manganese. We'll take now Mn plus 2 into Mn plus 3. We'll see. Manganese atomic number 25. So its electronic configuration is argon 3d5 4s0. 3d5 means off-filled configuration. 3d5 means off-filled configuration, we can say. Mn plus 3, argon 3d4, argon 3d4 4s0. So partially filled configuration. 3d4 means partially filled configuration, we can say. So off-filled configuration is converting into partially filled configuration in the sense how that potential is there, that we'll see. See the potential, negative potential. Manganese plus 2 into manganese plus 3 is a negative potential because off-filled is converting into partially filled. Then we'll take Fe plus 2 into Fe plus 3 will take. Fe atomic number 26. So electronic configuration is argon 3d6 4s2. Fe plus 2 means we have to remove 2 electrons, therefore 4s is 0. 3d6 means partially filled, we can say. 3d6 means partially filled. Fe plus 3, argon 3d5, argon 3d5 4s0. 3d5 means off-filled configuration. 3d5 means we can say off-filled configuration, we can say. 3d5, off-filled configuration. So partially filled is converting into off-filled stable configuration. So here you see that plus 2 into plus 3 minus 0.77. That means this negative tendency is, negative potential is less than manganese. This negative potential is less than manganese. For manganese more negative potential. For iron less negative potential. Why? Because Here off filled is converting into partial filled, whereas here partially filled is converting into off filled cell. Next we will see vanadium. We will take vanadium. Vanadium is a argon 3D 4s. We will take vanadium is a 23 atomic number, therefore 4s to 3d3. Now vanadium 2 plus we will take. Vanadium 2 plus means argon 3d3, argon 3d3 4s0. Vanadium 3 plus means argon 3d2 4s0. So now we'll see dd splitting. D orbitals undergo splitting in the octahedral complex and in tetrahedral complex. Octahedral means T2G and EG, T2G and EG. Now 3D3 we will fill in T2G like this. So we can say it is off-filled configuration. Here D orbitals will split like this. It is T2G, it is EG. Here 3D2, 2 electrons. It is not off-filled. It is off-filled, it is partially filled. So it is stable, it is not stable. Therefore, we will see the potential for this. The potential you see plus 0.26 volt. So the potential is a positive potential because their plus 0.26 volt is given. Why? We will see this off filled is converting into partially filled. Sorry. Why that one we have to see. Now we will compare with the titanium and chromium. In the titanium, if you see, titanium means here 3D2, here 3D1, partially filled, partially filled. Chromium, if you see 3D5, 4S1. So here 3D4, partially filled, 3D3, off filled. Therefore, for vanadium, potential is less when compared to chromium and titanium. Okay. Here partially filled into partially filled. Here partially filled into off filled. Therefore, here potential is more. Here potential is less. Here potential is more. Here both side partially filled. Here in both sides, in this case partially filled. Here off filled, here partially filled for this. For chromium, here partially filled, here off filled. Therefore, here potential is high, here potential is less, here potential is somewhat high. Like this is there. Next, we will say that. Next, we will go for the point. Aqueous solution of Mn plus 3. Aqueous solution of Mn plus 3 act as strong oxidizing agent. Aqueous solution of Mn plus 3 act as strong oxidizing agent. Aqueous solution of Mn plus 3 act as strong oxidizing agent. What does it mean? It is oxidizing agent means it undergoes a reduction. Sir, it undergoes a reduction like this. Here partially filled, here off filled. Therefore, it acts as oxidizing agent. Okay. Next, aqueous solution of CO3 plus act as strong oxidizing agent. It is oxidizing agent means it undergoes a reduction. That means CO3 plus converting into CO2 plus. CO3 plus configuration. CO3 plus means 3D6. CO3 plus means 3D6. CO2 plus means 3D7. 3D7. So, whether it is off filled or partially filled, how to say? It is acting as strong oxidizing agent, we said. Now, how to explain this? We are unable to say whether it is partially filled or completely filled like this, off filled like this, we cannot say. Now we'll see CO2 plus simple salts. CO2 plus simple salts is more stable when compared to CO3 plus simple salts. Okay, CO2 plus simple salts is more stable when compared to CO3 plus simple salts. But CO2 plus complex salts, CO2 plus complex salts is less stable when compared to CO3 plus complex salts. Okay, complex salts if you take CO3 plus is more stable. Simple salts if you take CO2 plus is more stable. Like this is there. So we are unable to explain this one using electronic configuration. Okay. So next point we will see aqueous solution of Ti2 plus, vanadium 2 plus, chromium 2 plus act as strong reducing agent, act as strong reductant. These are acting as strong reducing agent. That means they are undergoing oxidation. So now we will take Ti2 plus converting into Ti3 plus. Vanadium 2 plus is converting into vanadium 3 plus. Chromium 2 plus is converting into chromium 3 plus. Now E0 values, if you see E0 for this, E0 values we will see for these. Now see titanium positive, vanadium positive, chromium also positive. E0 values are positive, therefore these solutions are acting as strong reducing agents. So like in these points we are coming to know that we have to remember the points, isn't it? So experiment says what we have to see, as per that we have to remember. So aqueous solution of Ti plus 2, V plus 2, Cr plus 2 act as strong reducing agent. Strong reducing agent you have to remember. So now we will take Cr2 plus, we will take Cr2 plus, we will keep in acidic medium. What happens means Cr2 plus itself converts to Cr3 plus and we are getting hydrogen gas. So Cr2 plus in acidic medium converting into Cr3 plus. H plus is converting into hydrogen gas. Okay. Therefore, we can say aqueous solution of Ti plus 2, V plus 2, Cr plus 2 act as strong reductant. Aqueous solution of Ti plus 2, V plus 2, vanadium plus 2, Cr, chromium plus 2 act as what means a strong reducing agent, we can say. Okay. Next point, you see that Cr2 plus is stronger reducing agent. Cr2 plus is a stronger reducing agent. Stronger reducing agent than Fe plus 2. Cr2 plus aqueous is a stronger reducing agent than Fe plus 2 aqueous. Now, reducing agent in the sense itself undergoes oxidation. Therefore, we will convert Cr plus 2 into Cr plus 3. Here, Fe plus 2 into Fe plus 3. Reducing agent in the sense itself undergoes oxidation. So, we have written like this. For this configuration is 3D4. For this configuration is 3D3. 3D3 means T2G3 off filled. T2G3 off filled. Here D6. Here D5. D5 means off filled. Therefore, we can say, and we will see regarding this crystal field stabilization energy. We will see in Cr3 plus T2G3 we are saying. Why? Because D3. Here we will say T2G3 we can write like this. T2G3 crystal field stabilization energy is equal to what we can say means number of electrons into delta naught of T to G, delta naught of T to G. So the delta naught of T to G means 0.6. Therefore, how much will come in the sense T to G means 0.4 will come, 0.4. So 0.4 into 3, 1.2. This is what is the meaning means here like this will write. This is 0.4 delta naught. This energy is less than this barycenter. Therefore, it is having more stability. Therefore, minus we have to give. This energy is less than barycenter. Therefore, minus. So, crystal field stabilization energy is how much in the sense here crystal field stabilization energy is equal to minus 1.2 delta naught. For this case, we will see. For D5, we will see. That means Fe plus 3. Fe plus 3, D5 will take. D5 if you take here T to G, here Eg. So D5 means 5 electrons will write like this. So it is a barycenter. It is a barycenter. Now this one is a 0.4 delta naught. It is a 0.6 delta naught. So crystal field stabilization energy is equal to minus 3 electrons into 0.4 delta naught plus 2 electrons into 0.6 delta naught. So how much means 0? Crystal field stabilization energy is 0. Crystal field stabilization energy is 0. Crystal field stabilization energy is minus. Therefore, it is more stable when compared to this. So Cr3 plus is having more stability when compared to Fe plus 3. So Cr plus 3 stability is more than Fe plus 3. Therefore, Cr plus 2 is a stronger reducing agent than Fe plus 2. Like this we can say. Next we will say about stability of higher oxidation states. We will say stability of higher oxidation states. We are going for stability of higher oxidation states. Now we will take halides. We are taking halides. Now in the halides, if you see, fluorides stabilizes higher oxidation numbers. Fluorides stabilizes higher oxidation number. Why? For example, COF3 is having higher lattice energy and VF5 and CRF6 is having higher bond enthalpy. Now, so F minus stabilizes higher oxidation states. Now we are taking cobalt. Cobalt shows generally +2 and +3. The +3 stability of cobalt is highly stabilized by F minus among the halides because lattice enthalpy is more. Lattice enthalpy is directly proportional to charge of cation, charge of anion by distance between them square. So F minus is smaller size among the halides. So this value is smaller. So lattice enthalpy is higher. Therefore stability is higher. VF5 and CRF6 will take. Here vanadium is +5. Vanadium maximum oxidation number is +5. Chromium maximum oxidation number is +6. This maximum oxidation number of vanadium and chromium is stabilized by fluorine among the halides because fluorine size is small. Therefore, overlapping tendency is more. So bond strength is more. Therefore, bond enthalpy is more. Therefore, stability is more. Then we will take oxyhalides. Next, we will take oxyhalides. Oxyhalides. In the oxyhalides means MnO3F. Here Mn is +7. We can say VOX3. VOX3. Vanadium is +5. VOX3. Vanadium is +5. So more stable oxidation number. VOX3. Vanadium is more stable oxidation number. Manganese is a +7 oxidation number. Manganese is a +7 oxidation number. MnO3F, manganese is +7 oxidation number. VOX3, vanadium is a +5 oxidation number. Vanadium is a +5 oxidation number. Okay, so in the oxyhalides, oxygen and fluorine is there, both are stabilizing maximum oxidation numbers. Sir, now this we will, instead of saying it is this, we will say as a, sir, next point we will see oxides we will take. Next one is oxides. Oxides will take. Now, regarding oxides, oxygen carries -2. Oxides also stabilizes higher oxidation states than fluorine because oxygen can form multiple bond formation. Oxygen stabilizes higher oxidation states than fluorine, F, because oxygen can form double bond. Sir, next we'll take some oxides, TiO, vanadium oxide VO, chromium oxide CRO, ferrous oxide Fu. This basic nature we will see. Basic nature. Now we will take a Ti plus 2, vanadium plus 2, Cr plus 2, Fe plus 2. If you go like this, it is along the period, therefore size decreases. Therefore metallic nature decreases. Therefore basic nature decreases. Therefore, how the basic nature is there means basic nature is like this is there. So, next we'll take some more oxides we'll take now. Now we will take CRO is a basic. Cr2O3 is a amphoteric. Cr2O3 is amphoteric. CrO3 is acidic. CrO3 is acidic. CrO3 is acidic. Now, CRO with water. CRO with water, what we are getting in the sense H2CrO4, chromic acid. That is CrO3 with water gives chromic acid. H2CrO4 is called chromic acid. So CrO3 with water gives chromic acid, therefore it is acidic oxide, we can say. CrO3 with sodium hydroxide. With the sodium hydroxide, we are getting sodium chromate and water. So it is salt. It is base. Therefore, it is acidic oxide. We can call it is acidic oxide because it is reacting with the base to give what in the sense salt. So next, V2O3 basic. V2O3 basic. V2O4 less basic. V2O4 less basic. V2O5 amphoteric. V2O5 amphoteric. V2O3 basic. V2O4 less basic. V2O5 amphoteric. Now, I'll see. V2O4 react with acid to give VO2 plus and water. V2O5 react with acid to give VO2 plus and water. VO2 plus and water. V2O5 with base gives VO4 3 minus and water. It is oxo anion, it is oxocation. V2O4 is having less basic, therefore it is basic nature is there, so it is reacting with acid. V2O5 is amphoteric, so it is reacting with acid as well as basic. So, now we will see some oxocations and oxoanions. We'll see oxocations. TiO2 plus. Its name is O is called oxo. Ti is called titanium. Titanium oxidation number is 4, therefore Roman letter 4 ion. Then VO2 plus. This O is called oxo. V is called vanadium. Oxidation number of vanadium is plus 4, therefore 4 we have written ion. Its another name is what means vanadilyl ion. VO2 plus 2 times oxygen, therefore dioxo. V is called vanadium. Oxidation number of vanadium is 5 ion. Dioxo vanadium 5 ion. It is oxocations. These are. Now we will see oxoanions. VO4 3 minus. It is called vanadate ion. Vanadate ion. CrO4 2 minus. Oxoanion. Chromate. It is called chromate. MnO4 2 minus. It is called manganate. MnO4 minus. It is called permanganate. Cr2O7 2 minus. It is called dichromate. Cr2O7 2 minus. It is called dichromate. Next we will see oxidizing power of this oxocations, oxoanions. We will see. Now we will take VO2 plus. Its oxidizing power we will see. This VO2 plus is converting into what in the sense vanadium 2 plus. Here for this E0 value we will see, that is 0.36 volt. Now we will balance this one in acidic medium. Now oxygen is 2 times, therefore 2 water molecules. Hydrogen is 4 times, therefore 4 H plus because acidic medium. Now we will balance the charge, here plus 4, here plus 1, 5 plus, here plus 2, therefore 3 electrons. So VO2 plus takes electrons, therefore it is acting as oxidizing agent. Then we will take Cr2O7 2 minus. It is converting into Cr3 plus. For this E0 value 1.33 volt. Here we will balance this one. 7 oxygens, therefore 7 water molecules. 14 hydrogens, therefore 14 H plus. Now charge we will balance. Here minus 2, here plus 14, therefore plus 12. Chromium 2 times we will write. Here plus 6, therefore we will write 6 electrons. Therefore dichromate act as a oxidizing agent here. Then we will take permanganate. Permanganate is converting into Mn plus 2. Oxygen is 4, therefore 4 water molecules. Hydrogen is 8, therefore 8 H plus. Then electrons we have tried. Here minus 1, here plus 8, therefore plus 7 we can say. Here plus 2 is there, therefore 5 electrons. For this E0. For this E0 how much in the sense 1.51 volt. For this E0 how much means 1.51 volt we can say. Now we will say oxidizing power of these 3. Oxidizing power of VO2 plus is less than Cr2O7 2 minus is less than MnO4 minus. Oxidizing power like this is there. Oxidizing power of VO2 plus Cr2O7 2 minus MnO4 minus like this is there. Oxidizing power, sir. Next, disproportionation we will see. Disproportionation. Manganate MnO4 2 minus in acidic medium undergoes disproportionation to give permanganate and MnO2. Permanganate and MnO2. Manganate is converting into permanganate, oxidation. Manganate is converting into MnO2, reduction. Then Mn3 plus we will take. Mn3 plus undergoes disproportionation. Mn3 plus is converting into Mn2 plus by reduction and Mn4 plus by oxidation. Then Cu plus undergoes a disproportionation. Cu plus is converting into Cu plus 2 by oxidation. Cu plus is converting into Cu by reduction. Sir. Next, we will see colors of metal ions. We will see colors of metal ions. Now, Ti plus 3 aqueous exhibits purple color. Ti plus 3 aqueous purple. Vanadium 4 plus aqueous blue. Vanadium 3 plus aqueous green. Then vanadium 2 plus aqueous violet. Sir. Now see, oxidation state different means color also different because number of unpaired electrons will be different. Then chromium. Chromium 3 plus. Chromium 3 plus is violet. Chromium 2 plus. Chromium 2 plus is blue. Chromium 2 plus is blue. Mn3 plus. Mn3 plus aqueous violet. Mn2 plus aqueous pink. Fe3 plus aqueous. Fe3 plus aqueous yellow. Fe2 plus. Fe2 plus aqueous green. CO3 plus aqueous blue. CO2 plus aqueous pink. Na2 plus aqueous. Na2 plus aqueous green. Then Cu2 plus aqueous. Cu2 plus aqueous blue. So colors of metal ions in aqueous solution we have seen. Then magnetic moments we will see. Magnetic moments. Scandium 3 plus calculated value. Calculated value is how much means 1.73. Calculated value. Observed value how much means 1.75. So the calculated value and observed value no much difference. For which one in the sense for this scandium. Sorry. Next we will see that here we have seen colors of metal ions we have seen. From this we can come to know that Most of the transition metal compounds are colored. Sir, why transition metal ions exhibiting color? Because of dd transition. dd transition. Due to dd transition. What is dd transition? Now we will take a TiCl3. TiCl3 we will take. This TiCl3 is what in the sense colorless, will dissolve in water. Then we will get Ti3 plus aqueous. Now what is a color means purple color. Why is it so? TiCl3 solid is colorless. After dissolving in water, we are getting Ti plus 3 aqueous, it is purple because this Ti plus 3 is forming complex with the water molecules. So and so complex. It is octahedral complex. In the octahedral complex, this titanium 3D subshell is divided into two like this. One is T2G, another one is EG. In T2G, dxy orbital, dyz orbital, dzx orbital will be there. In EG set, dx square minus y square orbital, dz square orbitals will be there. Now, in this titanium plus 3, only one electron is there, that electron present in dxy, T2G1. When light is falling over here, this electron goes to EG. So, absorption. Then EG in the sense it is unstable. Therefore, it is T2G1, EG0. Correct? It is absorbing sunlight. Therefore, what happens means T2G0, EG1. So, it is absorbed in the VIBGR. It is absorbing certain wavelength. Remaining wavelengths will be emitted out, that combining together exhibiting purple color. So, this Ti3 plus exhibiting purple color because in VIBGR, particular wavelength is absorbed by this T2G in order to go to EG. Remaining wavelengths combined together called purple color. So Ti3 plus aqueous exhibiting purple color because of DD transition. Therefore, the transition metal ions exhibiting colors like this because of DD transition, we can say. Now we will take scandium plus 3. Scandium plus 3 is colorless because no d electrons. Titanium plus 4 is colorless because 3d is 0. Zn plus 2 is colorless because 3d is 10, completely filled. Completely filled means how it will go for DD transition? Cannot. So in these cases, what we can say means these are colorless. Sir. Now we will take a CrO4 2 minus. CrO4 2 minus is yellow color. Chromium is plus 6. Chromium plus 6 means 3d is 0. No d electron. So no dd transition. Then how it exhibits color? That we will see. So now we will say CrO4 2 minus. We can write like this. CrO4 2 minus. CrO4 2 minus we are writing like this. CrO4 2 minus we have written like this. Here double bond, here minus 1, here minus 1. Single bond, single bond. Here plus 6 oxidation number. Here 3d is 0. 3d is 0. What happens means here 3 lone pairs will be there. In this place, this electron jumps from oxygen to chromium. So what happens means chromium becomes plus 5, 3d is 1. This D can go for DD transition. Therefore, it is exhibiting color. This phenomenon is called charge transfer phenomenon. So chromate is having yellow color because of charge transfer phenomenon. Then dichromate is exhibiting orange color due to charge transfer phenomenon. Permanganate is exhibiting purple color due to charge transfer phenomenon. So here this chromate, dichromate, permanganate exhibiting color because of charge transfer phenomenon. Due to charge transfer, this oxygen -1 becomes -2, chromium +6 becomes +5. Okay. This is about colors of transition metal ions. In the next class, we will continue magnetic properties. Will continue.